Okay, welcome to this afternoon's lecture about verifiable C and how to use it to prove programs correct. And the title of this lecture is nice and intimidating, so let me explain to you the title. First, we want to prove programs correct. And you all know by this time how to prove programs correct. We write a little functional program. So there's add, which is a functional program over an inductive data type. And then here's a correctness property of add. We have many properties we want to prove about add, but here's one, that it's associative. So the nice thing about Coq is that when you prove a functional program correct, you can do it directly by induction over, the function argument. So how does the proof go? Well, we'll bring things above the line. We will do induction on the first argument, on A, and this gives us two cases, the O case. So let's look at the O case. If we simplify that, it just turns out to be beta eta equal. So we can prove that by reflexivity. And if we simplify the successor case, you see here we have a successor inside, and here we have a successor outside. But if we simplify by the definition of add, we get this, and then we apply reflexivity. And here's one of the most important and valuable features of a proof assistant. It doesn't let you make bad proofs. Okay, you forgot, right? It's very valuable that it accepts our valid proofs, but I can make a much simpler program that would accept all your valid proofs, so it also rejects the invalid proofs. Okay, so we remove that line. We rewrite by the induction hypothesis, and now it's provable by reflexivity. So that's nice. Proving program correct in Coq is easy, but let's prove C programs correct. Well, that's preposterous. Surely one should write pure functional programs in a language with a clean proof theory and prove those correct, which is true most of the time, right? But once in a while you have some specific demand for the kind of low latency or bounded resource programming that you get with C, or you want low-level interoperability with an industry standard language, or you want to write the runtime system for your beautiful functional language with the good proof theory. So some very small proportion of your programs you might want to write in C. Okay, so we want to prove C programs correct, so we need a program logic for doing it. We can't any longer just do direct induction on function arguments. We need to reason about program state or something. We could use Hoare logic, we could use some sort of abstract interpretation, but we'll choose Hoare logic. Now, we want to prove programs correct, not just safe, right? Out there in the world, there are static analyses which prove that the program doesn't crash. Well, some static analyses are sound, in which case, when they say the program doesn't crash, it's really true, and others are not sound, but still could be useful, right? So even, let's say, a sound static analysis will prove that the program doesn't crash, but we would like to prove that the program is correct, that it delivers the kind of result that it claims. So we want to prove that the program computes the right answer. And that will involve reasoning sometimes in the mathematics of the application domain. So therefore, the assertion language of our Hoare logic should be in an expressive general purpose logic capable of reasoning about the mathematics of any application domain. And for that reason, we choose Coq. We want to embed the program logic for C in Coq, so its assertion language is basically just Coq. Okay, C programs have data structures. We want to prove C programs that use pointer data structures correct. And 20th century Hoare logic isn't very good at data structures, so we will use 21st century Hoare logic, also known as separation logic. Okay, but these should be modular programs. And a well-known result from the 20th century is that abstract types have existential type. And that's a fancy, concise way of saying that the way you can reason about program modularity, where there are hidden representations and hidden representation invariants, is to quantify existentially over the hidden predicates for those invariants. And so we need a higher order logic that's capable of quantifying over predicates. We can't really do modular proofs about modular programs in first order logic. And so, I'll just remind you that first order logic you can quantify over base values. And that's the kind that SMT solvers are good at. And in higher order logic, we want to quantify over predicates. And, sometimes the SMT solvers can approach those proofs, but in general, they're not very good at it. So, higher order logic. Now, these modular programs sometimes pass functions back and forth or store functions in objects. So, we have an object with a method that takes a self parameter that's extensible from the object type, and that's a kind of contravariant pattern of use. Or in concurrent programming, we have a spawn function that takes as an argument the thread start function, and so in those patterns, it's helpful to have an impredicative higher order logic. So what does that mean? Well, when you instantiate the predicate, the bound variable of a quantifier in a logic that allows quantification over predicates, what kind of formula can you instantiate it with? If you can instantiate it with a quantified predicate, a formula that uses quantification, that can lead to paradoxes. So some logics stratify and say, well, at this level of quantification, you're allowed to instantiate with things from a lower level. But when we do object-oriented patterns, we don't want to calculate in advance at what level of stratification is this extensible object type. Programmers don't do that. We need logic that can reason about whatever it is that programmers are doing. So let's use an impredicative logic that avoids those paradoxes but can still quantify over predicates that you can instantiate by arbitrary, almost quantified formulas. And maybe I'll come back and talk about that later. All right, and they should be concurrent C programs. This is the 21st century. All of our computers are multi-core. I don't know, there's probably a multi-core computer in this presentation remote. And so we need shared memory concurrent programs. And for that, we need concurrent separation logic. But that's all right. Separation logic does quite well in concurrency. So let's prove concurrent modular object-oriented C programs that use pointers correct. And so therefore, we'll use a higher order impredicative concurrent separation logic embedded in Coq. But such a logic would be far too complex to trust its soundness. So we'll prove it sound in Coq with respect to the operational semantics of C. But the operational semantics of C is far too complex to trust as a definition. So we'll prove it sound with respect to the COMSIRT C-Lite operational semantics, with respect to which COMSIRT is proved correct. And if it turns out that that's not exactly C, that's all right. If you prove your program has some property in verifiable C, and you compose that proof with and you compile it with COMSIRT, so you compose with the proof of COMSIRT's correctness, then whatever language it happens to have been written in, it will have the end-to-end property that when the compiled program runs, it will have the behavior you proved. Okay, so we'll use a foundationally sound higher order impredicative concurrent separation logic embedded in Coq. But such a logic would be far too complex for users to actually use. Okay, so we will provide a proof automation system in Coq's lemma and tactic language to help users apply the program logic to their programs. And that is the verified software toolchain. And it has these components. It has, in the middle, the program logic. And there's a semantic model of that program logic built in Coq with which we do the soundness proof of the logic with respect to the operational semantics of COMSIRT C-Lite. And what that means is whatever properties you prove about your program in the logic, then the execution at the source level will have those properties. We compose that with the correctness proof of COMSIRT, and that means that the assembly language program, when it runs, will have the same properties. And then we have proof automation programmed in the Coq tactic language and lemma language, right? A lot of the proof automation is just well-designed lemmas that apply to your programs and applied biotactics. And that is called BST Floyd. Okay, so let's talk about program logics. We'll start with, I don't know, 1973 or something, 1971, Hoare logic. So a Hoare triple has a precondition that's an assertion about the state of the program at this point in its execution. It has a command, and it has a postcondition. So here, if x is greater than or equal to 0, and we run this command, then when we finish, x will be greater than or equal to 3. We could actually make a stronger postcondition than that, that's more accurate in some sense, but this is all right as a specification if that's the only correctness property you need, right? The correctness property you need determines your specification, not the most detailed, strongest thing you can prove about your program. And there are proof rules in Hoare logic that allow you to, let's say here, prove an if statement by means of proofs about the components of that if statement. So here, the if statement is correct with respect to precondition P and postcondition Q, but we can derive that if we can derive that with P and the loop test expression, that's a strong enough precondition to run C and end up with Q true. And P and the negation of the loop test is a precondition for D with postcondition Q. The Hoare triple means if the precondition is satisfied, then when you run the command, it is guaranteed not to crash, not to exhibit undefined behavior. And if it terminates, it will terminate in a state with the postcondition true. There are forms of Hoare logic that also guarantee termination, but verifiable C is not that at the moment. It's a logic of partial correctness. And of course, when you run a C command, it has different ways of exiting. It could break, it could continue, it could fall through normally, it could return. And so really the postcondition is a collection of postconditions for the different way a command could exit. Okay, so that was a brief review of Hoare logic. And now let's verify a program. This program is imperative destructive list reverse. So it's given a linked list P, and by the time it returns W, W should be a linked list that has the same head values but in reverse order. But the original linked list may have been destroyed or rearranged, so you can't really use P anymore. Now, when we prove things about data structures, we're going to use separation logic, which is a kind of Hoare logic in which each assertion predicates on a particular subset of the memory, of the heap. And we call these heaplets. So think of it as a part of the heap with a particular footprint. And this operator, separating conjunction, written with the star, means P star Q holds on a heaplet if that heaplet can be divided into two disjoint subheaplets such that P is satisfied by one of them and Q is satisfied by the other. Okay, so here's an example of a separating conjunction. It describes this data structure where X points to a con cell that holds 1 and Y points to a con cell that holds 2 and Z. So you can see the domain of the heap that satisfies the left-hand side is these two addresses, x.head and x.tail, and the domain that satisfies this is these two addresses, and then the whole assertion is satisfied on the entire heaplet. Notice also that between the two heaplets there's a dangling reference. That if you consider just this heaplet by itself, x maps to 1, y, which is just this guy, there's an out pointer that points outside of this heaplet, and that's perfectly all right. Okay, and we can run x.data gets 3, and when we finish, x points to 3, y, and y points to 2, z. This is already non-trivial. If we used the and here, in the ordinary logical conjunction rather than the separating conjunction, then we would have trouble reasoning about whether when we update x.data, does y.data also change? And to prove that it doesn't, we'd have to have the precondition not only that x contains this and y contains that, but that x is not equal to y. Well, in this case, we could do that because if x were equal to y, then x couldn't contain a 1 at the same time y contains a 2. But in general, we would have to maintain all sorts of anti-aliasing information. And so this is what the separating conjunction gives you quite elegantly, is the ability to reason about modifying one part of a data structure while the other is guaranteed not to change. Okay, so I think I said all this already. Now let's think about this as a linked list starting at x. Well, if it's abstractly a linked list starting at x, we shouldn't need y as a free variable. And indeed, we can take this assertion and quantify with an existential quantifier on y, and now we get exists y such that x maps to 1 y star, y maps to 2 null. And that describes this linked list, or at least this linked list of length 2. And now we want to generalize this to linked lists of arbitrary length. So we can do that with a recursive definition. P is a linked list representing the mathematical sequence sigma if P is the null pointer and the empty heaplet, right, empty memory, and sigma is the empty list, or there exists H, which is the head value, and sigma prime, which is the rest of the list, and Y, such that the original sequence sigma is H con sigma prime. P maps to H comma Y, that's this part of the picture. And separated from that, Y is a linked list representing sigma prime. Now, you know in logic, when you start writing recursive definitions, you have to be careful so that you don't get paradoxes. And so to demonstrate that we can be careful, why don't we just write this in Coq as a fixed point? And if Coq accepts this fixed point, it must be okay. So why does Coq accept this fixed point? Because this definition is structurally recursive on sigma. If sigma is a finite sequence, then this unfolds only a finite number of times. It's well-founded. Okay, and so this up here is just notation for what we might write here in sort of pencil and paper math. The existential quantifier of the separation logic is this capital EX. The maps to operator here is this data at predicate. Now, when theorists write their separation logic P maps to H comma Y, they conveniently leave out what kind of struct does P point to, right? How many fields does it have, and what are their types, and what are their names? And you know, when I showed you the program, I defined a particular struct. That's called struct list. And so if I'm going to start talking about P maps to X whatever, I should say this is a maps to a data at this type T struct list. This top here, it has to do with ownership shares, useful for concurrent programming, but let's just always put a top there for now. Now we can say what are the contents, the values represented by this data structure, and the fields are filled with H and Y. Notice that the type of this tuple depends on the value of this argument, T struct list. T struct list is a description of a C data type. So that's just a value. It's a value of type C language type. And this argument has a type that depends on this value. So we're using dependent types. That's all right. Coq has dependent types. Now, and finally, P is the address at which this thing sits. So fine, that's this, separated from Y is a linked list representing sigma prime. And in the nil case, that's here, well, this bang bang just injects a Coq proposition into separation logic. This double ampersand is the logical and, but in the separation logic, because the other thing was already taken for propositions. And then emp